So Vanakkam. So we will continue our lecture on engineering seismology. So last class we have been discussing about the seismic microzonation. Okay, so the different studies done on seismic microzonation in India. Particularly we have seen that even though there are so many people carried out seismic microzonation topic studies, but only the city which is worth to be climbed is Guwahati and Chennai Guwahati and Delhi microzonation and Bangalore microzonation. So we have seen that basically the earthquake create a lot of ground shaking related hazard, which includes like ground shaking directly, amplification of the seismic waves, liquefaction, landslide. So these are all the ground shaking hazard. Okay, so the microzonation is done basically to delineate the similar area which has this kind of effect or similar. Okay, so we also seen that the microzonation has carried out on macro scale and micro scale and nano scale. So macro scale we discussed the global earthquake model, GEM we discussed. So we have seen that how that models are useful. Particularly we have seen that those models they basically assess the exposure level of the infrastructure in the each country, particularly residential building, commercial building, industrial building, so that you know what is the risk and loss going to incur if such kind of earthquakes are coming, and what is the return period of this risk and loss for every year. So that is what we try to understand. Particularly they highlighted that taking a typical earthquake damage in the past in the country and data and models, and then they developed a user interfaceable maps, okay, where you can zoom in and find out each grid what is the value. They also given a risk financial loss associated, okay, with the damage and how much you can expect on each places. So the people who want to invest and do a business, so they basically get all these details from this map, and fatality rate also they included. So all those things are the part. We also discussed that the macrozonation basically gives you the wider perspective. So in the global level we have seen that global seismic hazard analysis carried out on 1992 to 1999. So where we have seen how the hazard analysis and other things are done. Then followed by the GEM 2014 to 2018, where we have seen the India map like North and Thimbajam data has been modified, and they have been using that and this one. We have also seen that it is a broaderly a country level estimation. Okay, it is not narrowed down to the each city level, because there is a lot of information need to go. So they also clearly mentioned that the fatality rate or the economic loss or the hazard index what they are given is not considered the tsunami, liquefaction, landslide, amplification phenomena which happens locally. Okay, so which is necessitates that if you want to prevent and plan properly and then execute something safer way in each city in India, there is a need for seismic microzonation of cities. So that is why we have seen that after Bhuj 2001 earthquake, and even the Jabalpur area has been taken as a classical example, and people have done microzonation of Jabalpur, and then the Delhi, Guwahati, these are all the regions where specifically done extensive work on this angle. So we also notice that there are many other people who do hazard analysis and other studies claiming to be a microzonation, but which is not really microzonation according to the methodology what we discussed. Okay, so we discussed that a microzonation is a delineation of area. Okay, so basically it's so the region will be subdivided based on the exposure of various earthquake effect. Okay, that is what we have seen. So with that definition, so the any grid or any area what you delineate, okay, that has to spell out what are the different possible earthquake is expected on this and how accurately that is assessed. So that is the main way the microzonation map has to be represented. Okay, so the global scale maps are macrozonations, not microzonation. When you come to the city level, it should be micro level has to be done. So today class, as I told you last class that I have done extensive work for the Bangalore region. So today I am going to discuss what I have done for the microzonation of Bangalore city, which was actually part of my PhD I carried out. This report also officially released by the MOES. So you can get the entire full report about details and all those things. So you can also see the related publication which I am going to discuss. So these are all the some of the publication which he published part of microresonation. So you can see basically these publications are updated, okay, from 2008 to 2010, the better improvement. From 2010 to 2013 there is a improvement. So you can also visit the website given here if you want to download some of this papers, soft copy, whatever I do, and also this website where to get lot of information. But note that the microresonation website was not updated long time, but I will be updating soon. Okay, so this is a reference we are going to discuss today, the microresonation aspect. So as we have seen that the microresonation, okay, consists of a 6 major component, which is like analysis and producing a map, and the 7th one will be the integrating all the results and then getting the final output. So we seen that the direct ground shaking at the bedrock level, okay, as we have seen that the GEM, global earthquake model, even estimated the hazard at bedrock condition. So similarly, the bedrock level estimation of the hazard is the first and most important for microresonation, which is applicable to all the city irrespective of where the city is located. Okay, so that step has to be carried out a first part. So which can produce a PGA distribution map and then synthetic ground motion and response spectrum and probabilistic and deterministic hazard level indication like 2% probability in 50 years, 10% probability in 50 years. So all those things. So we will be discussing this hazard analysis end of our lecture, how to do hazard analysis by deterministic and probabilistic with the case studies. Up to that we will be carrying out actually. So once you are done that, as I told you that the seismic waves, okay, travels from the bedrock, okay, when it comes to the soil the waves are get modified based on the soil static and dynamic properties. So that modification has to be captured. If you want to capture that, first you have to characterize the site and what type of soil it is present, what is the stiffness, okay, so what is the Young's modulus. So that kind of study is a part 2 as a site characterization, which will help you to produce basically the stiffness average map in the particular region, thickness of the soil at a particular region and other related issues, okay, other related parameters and rock depth and 3D modeling, all those data can be produced from the this kind of studies, okay, which is called as a site characterization. Once you are done that, by clubbing the hazard analysis and soil property, you can estimate and quantify how much the amplification and modification going to take in the region. So that is called as a site response studies, and which can be done theoretically as well as experimentally, okay. So using the data obtained from the step 1 and step 2. So in that third step you produce a amplification map of the region, PGA distribution at a surface level, at a different level considering the regional variation in the soil properties, okay. So then the response spectrum considering the soil amplification. So these are all the typical study. Then predominant frequency of the fundamental frequency and predominant frequency of the soil column, so that when you design your structure you should keep your structures not matching with the fundamental frequency of the soil column in the region. So these maps are produced as a part of step 3 analysis in the microresonation methodology, which was developed by IISc Bangalore, okay. So once you are done that, the amplified ground motion will cause us a permanent deformation in the soil. So when particularly on cohesionless soil where the particles are tendency to move very easily, so that analysis called as a liquefaction assessment, okay. The liquefaction assessment takes a input from the second and third part, okay, the amplified ground motion and soil data, and do the detailed analysis and identify which are the areas are liquefiable, which are the areas are non-liquefiable. The liquefiable again what severe it is, okay, the factor of safety is low, it will be very severe, it is close to 1, it is okay, more than 1 it is partially. So such kind of deviation should be done and the map has to be prepared a part of liquefaction assessment, okay. So this will be the fourth part of seismic microresonation. So mostly when the clay soil region liquefaction may not happen, other 3 will be fine, okay. So similarly once you have done the liquefaction, the regions or cities which is located on the hill, okay, so hilly terrain, So those kind of hilly terrain will cause us a additional hazard called a landslide hazard, which is due to the seismic activity. So the next step is to estimate a landslide hazard which is caused due to the earthquake, okay, and then map a landslide factor of safety or landslide hazard map saying that which are the landslide take place, what PGA kind of things. So that kind of map only applicable to the cities or regions which is in the hilly terrain. So then the cities which is next to the coastal region, as we have seen that the 2004 tsunami caused huge amount of the deaths and the financial loss in the east and west coast of India. So considering tsunami also part of the seismic zonations are very important for the cities which are lying on the coastal, particularly where there are some places even they install nuclear power station kind of things and all. So where they prepare a tsunami inundation map, okay. So how much tsunami depth you can expect, and then what is the, so the velocity it will hit, okay. So then the height of wave, so all those things will be taken and mapped in the tsunami hazard assessment. So it can be noted here that a regular other parameter assessment, you should consider the seismic data within the seismic steady area, generally 500 km for southern India and 750 km for the north India, which I will discuss why we take the such area for the study. And the tsunami assessment, you need to take a source, tsunamogenic source, which is up to 2500 km. That means if you want to do the tsunami hazard analysis of the Chennai coast, then you should consider 2500 km radius around that whatever fault and fold, so as well as the plate boundaries located on the seaside. Okay, so that was a very important. Once you are systematically estimated all these parameters, the next step is basically to integrate all of them appropriately based on the weights and ranks, and finally develop a zonation map, okay. So which is called as a microzonation map, which reflect a hazard index value. So these hazard index values are, once you decide that, you will know that which are the places are highly risk, which are the places are low risk with respect to considering all the possible seismic hazard. Then you take a account of the building in that area, okay, how much buildings are exposure and what is the vulnerability. Okay, so sometime your hazard may be high, the building is considered and designed for earthquake, then it will be low vulnerability. Okay, so like that you should do a systematic analysis of the study a building and map their vulnerability case scale. So that is a vulnerability analysis. Once you map your buildings, then you will know how many people living in that building, what is the income per capita income. So based on the vulnerability and hazard, you can multiply both, you will get a risk. So generally the vulnerability, high risk will result, high vulnerability, high hazard value will result in the high risk. Okay, so the risk could be higher, risk will be higher, your hazard is high and your vulnerability also high. Okay, so both are high. So the risk will be sometime moderate, your hazard may be high, but vulnerability will be less. Okay, the buildings are safe. Okay, so similarly the risk vary with like you will have the low hazard and vulnerability high, then your risk will vary. So this is a composite. So this risk will give you, okay, this risk, seismic risk will give you how much financial loss you can expect, okay, how many people will die, what are the level of disaster you can expect due to the typical earthquake. Okay, so this was very important particularly for the disaster management planning and disaster, so minimizing the disaster. Okay, so that's why the macro scale map, soon after they prepared a bedrock level hazard values, they also estimated the exposure and the number of fatality and financial loss expected from the different earthquakes. Okay, so this is the whole objective of the micro zonation mapping and the steps involved on that. So which means that the any microzonation study which consider in a particular region should have a systematically listed parameters which has to be considered in the mapping hazard index value. Okay, so we will not talk about the risk and vulnerability, only we will talk about up the zonation mapping, okay, for the discussion here, but we stop at only estimation up to the hazard analysis, because beyond that you need a geotechnical knowledge from the civil engineering, so which is generally not minimum requirement for this essential requirement for this course. So we are only stopping at hazard values, okay, which we will be discussing in the future classes, how to estimate hazard. So as I said that, so you will be estimating a direct hazard, so in the form of deterministic and probabilistic, and then amplification from this one, and then which is also related with the soil thickness. So then the soil stiffness, liquefaction factor, and then predominant frequency, elevation level, drainage factor, and topography. Basically these parameters, okay, so all clubbed together will represent somewhere the site effect or amplification. So here we didn't include a landslide hazard as well as the tsunami, okay, because this is the case study of Bangalore, where the landslide and a tsunami is not possible, okay. So that's why we didn't include a landslide and tsunami part of the theme and weights needed for this one. So in this entire process we should do it on the geographical information system for the seismic zonation. So why we have to do the geographical information system? So the GIS has a capacity to store, manipulate, analyze and display large amount of the required spatial and tabular data. So the GIS basically is a mapping tool, okay. So whatever you are seeing a Google map, so this kind of map where can be produced in GIS, this has a capacity to store, okay, and manipulate and analyze and display, and then the data in the spatial and tabular form. So that means you can give input as a spatial as well as a tabular form. This will store your data and manipulate. So that is how the manipulation is taking place. I don't know how many of you notice that when you use your Google map, okay, so when you use your Google map in your mobile, so you go like somewhere, one to grocery shop, market, and then the movie theater, something like that. So after a month or a week, Google will tell you these are all the places you visited, you want to rate, okay. So it will tell you, then based on the your purchase, if you take some photos or something, like if you purchase in the visit some particular shop, it will remind you that in this shop there is a something cheaper you want to buy, okay. So such kind of ad, advertisement, manipulation and process and analyze data and display, okay, so to the user. So that kind of the larger activity is possible in the GIS in the spatial as well as tabular form. Spatial form means a data form which is map form you can give, or a tabular form. So one of the most important features of geographic information is data analysis on both spatial and tabular form. So the tabular form is basically non-graphic data, spatial form is graphics data. So the final map can be developed using the analytical hierarchy procedure in GIS form. So this analytical hierarchy procedure we will discuss in the next slide. So which is the user friendly way you can describe the weights of the parameters, okay, analytical hierarchy process, okay. That so the analytical hierarchy process is a multi decision method that uses hierarchic structures, okay. You can rank parameters based on the importance, then develop a priority and alternate based judgment of the user. So which was developed by the Santee in 1980s. So the first time the analytical hierarchy procedure are incorporated in seismic zonation work by the North for the Sikkim microzonation work, okay. Before that people are not using this kind of technique in the preparing zonation map in India, okay. So that is for your information. So the analytical hierarchy procedure, okay. So Stantee's analytical hierarchy process construct a matrix of pairwise comparison ratios between the factor of the different earthquake hazard parameters. So the earthquake hazard parameters, what we mean here, the bedrock hazard, amplification, liquefaction, landslide, tsunami. So these are all the factors which is responsible to cause earthquake hazard and death and damage. Those are all the parameters called as a earthquake hazard parameters. So this will take a basically constructs a matrix pairwise comparison and take ratio between these factors. So that is a very important in the analytical hierarchy process. The construction matrix shows the relative importance of the each earthquake parameters based on their weights. So, allocation of the weights identical to the EHP depends upon the relative importance of the factor and the participatory ground decision makers. So, this assigning a weight of particular factors depends upon the user or participation group. For example, some place the tsunami will be given higher weight, some place the landslide will be given higher weight, some place the liquefaction may be given as a higher weight, some place the ground shaking hazard can be given as a higher weight. So, this depends upon the group decision makers who is involved in the making a analytical hierarchy process. So, if for example, 9 earthquake hazard parameters are selected, which you have discussed in the last slide. So, in the scale of 1 to 9, so the one meaning that 2 factors are equally important, okay, and the 9 indicating that one factor is more important than a other. Okay. So, the reciprocal of 1 to 9, 1 by 1, 1 by 9 shows one is less important than the others. Okay. So, that is how the analytical hierarchy procedure works. So, then the individual normalized weights of each, okay, so EHP are derived from the matrix developed by the fairwise comparison between the factors and EHP. This operation is performed by calculating the principal eigenvector matrix. The results are range from 0 to 1, the sum add up to the 1. So, finally, even though you prepare a different ranking and then the assign a different weights to the each parameter, you make a eigenvector estimation and make each parameters as a normalized weight and sum of the parameters finally to the unity. That means, the highest hazard index can be expected on any zonation map should be unity. Okay, the lowest will be the 0. So, in between it varies depends upon the its level and position and all those things. So, the weight of each attribute can be calculated by averaging the value of each row of matrix, which we will discuss in the next slide. So, these weights will be sum to 1 can be used deriving the weight sum up rating, a score of each region cell or polygon in the mapped domain. Okay, so, since EHP varies significantly and depends on the several factors, they need to be classified into 2 ranges of type, which known as a features of layers. Each earthquake hazard parameter features are rated or scored within the EHP, then this one. So, we have seen that each parameter would describe, but that parameter as a sub range. For example, if you take a PGA estimation, as you know that one place the PGA will be 0.01 low, another place 0.01 to 0.05. So, something like that you will have a different group depends upon the region. So, this each individual group within the earthquake hazard parameter need to be ranked and normalized ranking weight has to be estimated. So, that is the formula where you can estimate a normalized the weight of the each parameter. You can see that. So, the R is the ranking of individual parameters, R minimum is the lowest ranking, maximum is the highest ranking, then you can get a normalized weight using the this formula. Okay. So, this will give you the normalized weight. So, the earthquake hazard parameters can be broadly classified as a 2 category. So, one is the geomorphological attributes, another is the seismological attributes. So, what is the geomorphological attributes? Geomorphological attributes is a parameters which are responsible from the geology and morphology of the region. So, the geology means like the soil formation, okay, soil elevation level. So, that is the geomorphology. Okay, the soil type, it is a geology. Okay, so those are all the geological attributes, okay, which is varies like bedrock depth. So, these are seismological attributes are the parameter which is estimated considering the earthquake. Okay, so for example, amplification, predominant frequency. Okay, so then the liquefaction where you need earthquake data as a input to arrive these parameters. Okay, so this is the seismo. So, the entire parameters whatever we have, we can group as a geomorphology attributes and seismological attributes. So, the weight of each attribute depends upon the region and decision maker, which we have discussed earlier. Example, flat terrain has a 0 weight for a landslide and a deep terrain has a highest weight for the site response and liquefaction. You can see here. So, but if you want to take a landslide, so the parameters which is given for the flat land is 0. Okay. At the same time, if you want to do the liquefaction and site response, deep soil is a favorably high weight. So, this is how the ranking and weighting has to be assigned. So, the earthquake effect depends upon the ground geomorphological attribute considering the geology, geomorphology, geotechnical information. The parameters of geology, geomorphology, soil thickness, rock outcrop depth are the most geomorphological attributes. So, these are all the parameter which varies with respect to the your with respect to the geomorphology, geology features. The other attributes which we have discussed, that the seismological attributes, which is the function of earthquake occurrence or earthquake data, okay, the peak ground acceleration, which may be from deterministic, probabilistic, amplification, which is again earthquake data as a input, site response, predominant frequency, liquefaction, landslide, okay, due to earthquake, and tsunami. So, these are all the parameters for the seismological attributes. Okay, this is the seismological attribute where you can see that these are all the function of earthquake data. So, these parameters has been ultimately combined, okay, such that you can generate a final hazard index value, which is integration of all these parameter depends upon the weights and rank of the seismological and geomorphological theme. So, the theme weight has been assigned based on their contribution to the seismic hazard at a particular region. So, based on the past earthquake, you will get the idea like what are the parameters are contributed more hazard from the isosysmal and intensity map. So, based on that you can decide that this is the parameter where you can assign a more weight and less weight, or based on the experience in case if you do not have the much data from the previous year. So, once the identical weights are assigned and normalized weights can be calculated based on the pairwise comparison matrix. Okay, so, the once you weight has been calculated for each earthquake hazard parameters. Okay, so, then you can estimate a rank, assign a rank, okay, rank of each parameters division subdivision, and then calculate a normalized rank, okay, within the parameters. So, that is what you will be getting. Then you can multiply all of them systematically and then estimate a your hazard index value. So, how to estimate a pairwise matrix I was telling you. So, this is actually you take a 9 parameters which we discussed earlier, and this is how. So, you can divide by the each parameter by its own parameter in the first. For example, PGA, okay, so the which is assigned as a 9. So, 9 by 9 PGA, amplification 8, so divided by 9, so it's 7 by 9. So, like that you can see the unity in the con. So, you can prepare this kind of this one, and finally you arrive a weight, okay, based on the normalized value of each weight systematically calculated. So, this weight will indicate that how each parameter is given a weightage in your final hazard index value. Okay. So, this is about the individual parameter and its weight estimation. We have taken a 9 parameters here. So, if you cumulative will be unity basically. If you cumulate and see, you can get the unity of the values. So, once you are done that, as I told you that each parameter you will have a subgroup division. For example, PGA. PGA can be divided depends upon the value range produced in the region. For example, this particular region, this is the 4 classification we can get as the PGA varies from this to this. Okay. Then each one you will rank, okay, 1, 2, 3. The highest rank is given for the more hazardous, dangerous value. So, 4, 3, 4. Then you estimate a normalized rank using the formula what we discussed. You can see that the ranking, okay, so like this. So, similarly amplification factor, this is a typical example. So, this can be repeated for 5 group, 4 group, 2 group, 3 group, depends upon the number of group what you use on each earthquake hazard. So, once you are done that, finally the hazard index map can be developed by multiplying the weight and rank. Okay. So, that means each grid point you know what is the PGA, correct. So, you know what is the weight of PGA which is estimated as per table, it is 0.2, and then if this value is I got a 0.44, my ranking will be, so here you can see So the 0.1 to this one, so 2 my ranking and 0.33. So this will be 0.2 into 0.3. So like that one parameter. Similarly, the other amplification. So each grid, all the parameters whatever we estimated, multiplied and added and divided by the sum of the weights. Generally this is a unity. So you will get a value. That value is called as a seismic hazard index. So this hazard index can be estimated two cases. One is that deterministic hazard index, where the worst scenario for the one earthquake, and the another one the probabilistic hazard index. So as we have seen that the global seismic hazard map program, they use a probabilistic way. Here also when you estimate a PGA with a different possibility of probability of exceedance in given period, then you get a your microzonation map also deterministic and probabilistic. Okay. So this microzonation map, okay, is a map of zonation of the each region which represents all the possible scenario in the region. So this is a methodology detailed discussion of how the each hazard component will be taken, the weights will be taken and ranking will be taken. Okay. Then finally how the hazard index values are estimated. So yesterday we have discussed about the hazard index value when we are talking about the microzonation of some of the Indian cities and all those things. Okay. So now next we are going to discuss how this can be really applied for the microzonation of Bangalore in the next class. Okay. So thank you very much for watching this video. So we look forward again in the next class. Thank you.